Welcome, everybody, to your free GMAT Prep Hour. My name is Reed Arnold. It is, believe it or not, November 10th of 2022. We're already on the last stretch of the year. Welcome to another free prep hour. If you are looking for other free GMAT prep, Manhattan Prep has you covered. You can try the first of any live course for free. That is 1/9 of the entire course, over 10%. And as I always say, there's no reason to pass that up. Even if you have no intention of signing up, we cover some big stuff in class 1, how the test works, how it's graded, how to study, data sufficiency, which is the topic tonight, but we go into data sufficiency and some strategies there. Sentence correction, we give a good overview of that question type. So it's just a really rich, dense, important lesson that you can get free of charge. You can also try the first session of our Interact course. That's our self-paced video course. Follows the same syllabus as the class itself. So if you're looking for material on data sufficiency or how the GMAT is scored or sentence correction strategies, you can get those videos for free. See if that product is something you would like. But again, whether you intend to buy it or not, it's just a good resource that you can get free of charge. There are these free prep hours, which you can find the recordings on YouTube. And at this point, honestly, we have a library so full you can get your own. You can get more than a full course worth of material from all the free prep hours that are posted. So if you're looking for great instruction from Manhattan Prep instructors, it is there. We also have Foundations of Math workshops twice a month. We hold these. These are, again, free of charge. We talk about math in a way that not just is on the GMAT, but in a way that the GMAT rewards. So we go to those core foundational structures, those core foundational concepts that GMAT math is built on, and we really break them down and build them back up in a way that the GMAT rewards. It's one of my favorite classes to teach. I first took it having gotten a 760 on the test and having taught the GMAT for several years. And when I took the Foundations of Math course in order to teach it, I learned some tricks and some things that has changed how I think about math. And so I just think it's something that anyone could benefit from. So if you're looking for that, you can check our website, manhattanprep.com/gmat/resources. So today's lesson is a spinoff of a previous lesson. If you look on in our free GMAT Prep Hour library on YouTube, you can find a video called Inference, Chains, and Problem Solving, where we talk about a review session, not a review session, excuse me, a review tactic for problem solving questions that lays out step by step, that asks you to lay out step by step the different inferences a problem solving question requires to go from givens to answer. Okay. And it's really meant to get you thinking linearly, like really laying out each step of the process so you can see what that whole process looks like. You get a sense of how many inferences you need to make. And what this also helps you do is really pinpoint which inferences you found you struggled with on that problem. Where in that problem did something gunk up, to use the technical term? And there are two kinds of inference mistakes that happens. And in many ways, every mistake you make on the GMAT can be diagnosed as one of these things. Either you made an inference you should not make, or you didn't make an inference you should make. And so what this process really helps you do, really asks you to do, is lay out each inference. After you've done the question, after you reviewed the question, this is for when you're really trying to build the logic of the problem, but it gets you really thinking linearly in an organized, analytical fashion. So you can see every step, okay? And you can really pinpoint where in these steps do I feel most uncomfortable, right? Which of these moments is most sticky and why? Or did I make an inference I shouldn't make? Did I leap from something to something that I shouldn't have? That was in terms of problem solving. And just as a reminder, let me give you an example of what we did in that session and what I mean by, you'll get to see an inference chain here. So take 2 minutes here and work on this question. And then I'll show you what it would look like to build an inference chain when reviewing this question. That is 2 minutes. If you have an answer, go ahead and send it in the chat. If it's a question mark or a guess, put a question mark by it. That's completely fine. Thank you, Jocelyn. Question mark, that is fine. Just a reminder for this test, everybody, you're going to need to guess on questions in the actual exam. And I just want you to know if that feels like a failure, you're not going to be in the right mindset for this thing. You need to know that that happens, laugh about it or whatever you can do, and then just move on to the next question. It is by design that this will happen. And if you feel like a failure because you had to guess on a question, you're going to feel like a failure way too often on this test. And it's really, mindset's it's an important part of the game. And keep a good mindset here. You have to guess, okay, well, shoot, guess, move on. And then when you're studying, guess and then review it and learn from it. That's totally fine. Also, work and rate questions are just notoriously difficult. There's something that students, including myself, by the way, I think if you'd given me this exact question the day I got a 760, I don't think I would have been able to get it. I really struggled with work and rate questions. So you're allowed to have some weak points and still get a great score on this thing, just so you all know. Since then, and since teaching, I finally learned how to do these things. But even when I started teaching for a few years, for a few weeks, it was a little iffy until enough students brought it in. I was like, okay, I need to learn how to do these really fluidly. And I learned the thing that really helped me get these right more frequently. So what I do when I have a question like this, I have my A and B situation when they're working simultaneously. I have my A and C situation when they're working simultaneously, and I have my B and C situation when they're working simultaneously. And I'm just going to build the three scenarios using the standard work equals rate times time equation. And what's happening here? What work are they doing? They are filling a tank. So there's one tank of work done, and that's true in every situation. We're always filling the same tank. And I'm asked about what happens when they all fill the tank. What happens when A plus B plus C are all in the game filling this tank? Okay. Well, what do I know about A and B together? Well, their time is 6/5. And it's important that you don't mix up time and rate, but they can fill the tank in 6/5 of an hour. And that actually tells me that their rate is 5/6. They do 5/6 of the tank in 1 hour, because rate times time needs to equal 1. I'm going to do the same thing for when A and C are working together. Well, when A and C are working together, they fill the tank in 3/2 hours. That means their rate is 2/3. They do 2/3 of the tank every hour. And when B and C are working together, they do the tank in 2 hours. That means that working together, they do 1/2 the tank every hour. And here's the crucial insight I finally specified to make these questions more manageable. When things work together, when individual items or machines or people, when they work together, what you can do is add their individual rates to get the combined rate. Now, this one's a little bit tricky because I don't ever have any individual rates, right? I don't have A, I have A plus B's rate. I have, this is A's rate plus B's rate. And this rate is A's rate plus C's rate. And this rate is B's rate plus C's rate. So I don't ever actually have individual rates. I only have sums of their rates. But if I add those up anyway, what I'm going to end up having, it's like if I had 2 A's, 2 B's, and 2 C's. If I add 5/6 plus 2/3 plus 1/2, that's like having 2 machine A's plus 2 machine B's plus 2 machine C's, where each variable is the rate of that machine. So what this gives me is 2 times the rate, if I factor out, 2 times the rate of A plus B plus C. And what does that equal? Well, that equals 5/6 plus 4/6 plus 3/6, which equals 12/6, or 2. So 2 times their rate is 2. This isn't right. I made a mistake. 5, 9, 12, 6. Perhaps I haven't. If you see an arithmetic error, please let me know. 5/6 plus 2/3 plus 1/2. 5/6, 4/6, 3/6, 12/6. Okay, so yeah, their combined rate is 2, so their individual rate, I'm sorry, their combined rate twice is 2, meaning one of their combined rate is 1, meaning that if I want to get their time, I can plug in 1 times 1 and get an answer of 1. Still not totally convinced I didn't make a mistake there, which, hey, that happens. I'm less concerned about the actual math today, even though I know we want to get the math right, but that's really not the purpose of today's lesson. Even if I made a math mistake, the general process here is the one you would use. And that is what I'm interested here, because what I would do is, if I did this question and struggled with it and studied it and figured out, oh, okay, hold up, I can set up each individual thing and get their rates. I can add those rates to get this like combined rate. What can I do with that combined rate? Oh, I can use the combined rate to get their combined rate when they're each just alone. The combined rate I get is 2 of each. Well, what if I just have 1 of each? Okay, cool. So math, I understand that, but here's where the logic chain comes in, the inference chain. And I lay out what is given, and I make my inferences from that. And I go from what is given to what is asked, the time of one of these working together. Okay, and so I have time A and B alone, and then I got the rate of A and B together. I'm sorry, the time of A and B together, that gave me the rate of A and B together. That's just using the work rate time equation. What you can do is like specify how you make these inferences, right? This is based on work equals rate times time. So are these. These are all work equals rate time equations to get their rate. I have a question, will work always be 1? By the way, if you have a question, go ahead and type in the chat. There's like a question and answer box, but it's a little bit harder for me to see, so I might miss it. But I have a question, will the work always be 1? You can kind of pick that for yourself. I think it's often fine to do one job. But you can also kind of pick it. You can say like, well, how big is this gallon? I don't know. Let's say it's what works with 6/5 or what works with 6/3 and halves. Let's say it's 6 gallons, or let's say it's 30 gallons, right? You can kind of pick how much you want the work to be. Marilyn says, is this type consistently asked? Depends what you mean by consistently. I wouldn't say it shows up every test, but I would say it shows up every 2 tests, maybe every 3. Some sort of a rate question will be asked. Whether it will be a work together rate question, that's less consistent. But it's common enough that, you know, a little bit of practice won't hurt. But again, I would have missed this question the day I took the test. I might have just missed it today because I'm still not so sure about my math. But these do show up. Yeah, so Andre's asking, why add the rates and not the times? Well, think about it this way, Andre. If it takes me 1 hour to do a job and it takes you 2 hours to do a job, are we going to take 3 hours to do the job together? Why would it take us longer to do the job together? That wouldn't make sense unless we're suddenly way more inefficient. We distract each other when we work together, right? But as long as we're staying to our regular pace, if I do it in 1 hour and you do it in 2 hours, we should actually be done in less than an hour. It should speed up the process. Okay. And so the game is, if I paint 3 rooms an hour, is it because rate is the best equivalent measure? Well, again, if I paint 3 rooms an hour and you paint 2 rooms an hour, together we paint 5 rooms an hour. It's a little bit clearer when it's not in fraction mode, but Just think about if I do this number of things in an hour and someone else does this number of things in an hour, then together we get that much done in an hour. And if a third person comes in, add their rate to our rates. Okay. So any arithmetic mistakes aside, right? What you do is you really look at this thing. You study the question, you figure out how it's done, then you kind of lay out, okay, where do I see inferences? Where in the explanation that I now understand, where do I see inferences being made? Oh, I see that they use the time of A and B together to get the rate of A and B together. And they use the time of A and C to get the rate of A and C, and they use the time of B and C to get the rate of B and C. And then they took all of those rates and they got the rate of two A's, two B's, and two C's together. And you can really look like, okay, hold up, that inference, that freaks me out. I got to really think about that one. How does that work? Or some of you are asking right now, even like, okay, they get the rate of A and B together, but why even get the rate? This first inference is like, but what's even happening there? So you can really pinpoint what part of the process is most stuck, most gunky, least smooth. Then you can work on that particular thing. You can go to problems that test that particular subject, like work together questions. You can make your own questions, make your own scenarios where Jack builds 4 chairs a day, and Jill builds 3 chairs a day, and so together they build 7 chairs a day. So you're thinking about adding rates. Okay. Jocelyn says, let's say I understood it, but I know it'll take me over 2 minutes. Do I just guess regardless? Over 2 minutes is okay. 2 minutes is your average. If it's going to take over 3:15, it's probably better to just guess. But if you feel pretty confident that you can get it in 3, go for it. And if you're a little bit ahead, definitely go for it. But yeah, once it starts like, man, I could do this in 5 minutes, well, then don't do it. That's not the game you're playing when you take the GMAT. Point is here though. Here's the thing the thing we're going to talk about today is when you study a question, one review tactic is to lay out an inference map and space and figure out where each inference is. And again, figure out the ones that give you the most grief. Now, this is problem solving. And again, there's a whole video on this stuff if you want to watch it. Today, we're talking about data sufficiency and how this might look with a data sufficiency question. And data sufficiency is a very weird GMAT specific question type. Okay. It always looks like this. There's always a question up top, 2 statements, and then these 5 answer choices in this order with this language. And the idea in data sufficiency is that you were trying to figure out where in these 2 statements, where is there enough information to answer the question that is asked, or is there not enough information to answer the question that is asked? And that's not quite the same thing as actually trying to get to the answer of the question. Now, you often will anyway. You often will get to the answer anyway, but that's not even really the point. The point is knowing that you could get to the answer. And just like there are 2 kinds of inference mistakes in problem solving, not making inference you should make and making inferences you shouldn't, there are 2 kinds of data sufficiency mistakes. They're saying that something is sufficient when it's not sufficient, and they're saying that something is not sufficient when it is sufficient. If you say that information is sufficient, you've probably made an inference that is not actually allowed. You have jumped from what's given, or you've overlooked another possibility. So you're making that there's only one possible world when really you could infer that there are several possible worlds. If you say that something is not sufficient when in fact it is, you probably haven't chased the inference chain far enough, either because you didn't see how to make an inference or you didn't even see that an inference could be made. But you can study and review a question in order to in order to, similar to problem solving, figure out where in the process your inferences went awry. So let's try a data sufficiency question here. We've put a shortcut box to remember the answers here. 1, 2, 10, 1 alone, 2 alone, together, each, not enough. Okay, so take a look at this question. This is an official GMAT problem. And then we'll talk about how to do the question, and we'll show how an inference map could be made from this. It's 2 minutes. If one answer in, go ahead and make a guess if you have to make a guess. If it's a question mark, that is completely fine. There's 3 C's. I have an A, 2 A's. Have a B. No worries, Alex. It's okay. All right, let's call it there. So if I'm doing this question, layout, okay, Jack and Mark both received hourly wages of 6%. So we have a 6% increase on their wages, and their wages, I'm going to just call it Jack and Mark, for Jack's wage and Mark's wage. And I want to know, after this wage increase, how much more was Jack's wage than Mark's? And I could set up some equations, right? I could say, okay, 1.06, 1.06 J minus 1.06 Mark. That's what I want to know. Question mark. What is that? And this is actually a good opportunity to do a common data sufficiency tactic to rephrase the question a little bit. If I factor out the 1.06, I want to know what 1.06 J minus M is. What I'm going to actually do here is put my work, hello. Is put my work over to the right so that we can see the chain and compare it to the work that I would do. But what I would notice at this point is that to answer this question, I really need to know what Jack minus Mark's wage currently is. If I know that, I can increase that by 6%, and that will get me how much more Jack's wage is after the wage increase. This is asking what we call for what we call a combo. And this is a common GMAT game. Yes, to know the answer to this question, if I know Jack's wage and I know Mark's wage, raise those by 6% and you can answer the question. But technically, I don't need that. I need to know what Jack's minus Mark's wage is currently. I really need the difference. If I have the difference, I can answer the question that is asked, which is how much more, not how many dollars. And statement 1 tells me before the wage increase, Jack's income or Jack's wage was $5 more than Mark's. So J minus M is 5. And that actually, I can just plug that in right here and answer the question. That is sufficient. And statement 2 tells me that the original ratio of Jack to Mark is 4:3. And okay, that could be 40 minus 30. Or it could be 20 minus 15. And I could get different original differences, which would get me different final differences. And so this would not be sufficient. The answer would be A. Okay. Now, to lay this out, first off, ultimately on a data sufficiency question, you're wondering, is there always one answer to what is asked, or are multiple possible answers possible? In a value question like this is asking for a number. How many more dollars was Jack's wage than Mark's? That's a number question. That answer would be a number. Well, there's 2 possible outcomes that I'm curious about. If there's one possible value for the difference between Jack's and Mark's new income. If this is where I end up, the answer or the situation would be sufficient. If I could get more than one possible outcome to how many more dollars Jack's wage is than Mark's, this would be insufficient. So ultimately, I'm wondering which of these outcomes is the case in the data efficiency problem. And the key insight here is done before I really even get to statement 1 alone. If Jack's and Mark's wages both get a 6% increase, then the difference between Jack's and Mark's wages gets a 6% increase. If I'm used to something like this, I might know that kind of intuitively, but I can also show that algebraically. That's what this algebra shows me. That's the inference I make here. And then statement 1 tells me that before the increase, Jack's wage was $5 more than Mark. Well, hold up. If I take that and I say, hey, okay, if the original difference was $5 more, and the difference between them increased by 6%, then after the increase, Jack's wage was 5 times a 6% increase dollars more than Mark's. And the beauty of data efficiency is I don't technically need to do that math. If I do, it's going to be $5.30. But the point is that this gets me a single answer to the question. There's only one possible value that answers this question, $5.30. Notice the inference I can't make. I can't make how much money I don't know if it's 100 and 105 or 15 and 20 or 45 and 50. I have no idea what their actual wages are, but I know their difference is 5 and then it becomes 530. In many ways, data sufficiency is about, can you build an inference chain in general? Does the inference chain complete to one outcome? And this does. This gets to 530. That is a sufficient situation. If I make an inference chain for statement 2, I know that their ratio was 4:3. Well, I mean, I could just, this is just testing cases. If the ratio is 4:3, it could have been 20, it could have been 400, 20 and 15, 430, and 300. Which means the difference could have been 5, or the difference could have been 100. Which means the actual dollar difference after the increase could have been 530, or it could have been 106. There's multiple possible values for that final step. So statement 2 is not sufficient. I cannot get to one single answer. Using a more just straightforward algebra approach, or just kind of a proportional understanding, if the difference between them increased by 6%, the ratio actually stays the same. All I know is that afterwards, their ratio is still 4:3. There's many numbers that fit that ratio. So I can't actually answer what their actual dollar difference is. Now, several of us chose C. And that is what we call the C trap. This is a very common GMAT trap. And it's because there is an inference chain that you can build from these pieces of information. If I know, and let's just look here, if we look at statement, if we just look at statement 1 and 2, I know that before the increase, Jack's wage was $5 more, and then I get their ratio. I can synthesize that information and make an inference that Jack made $20 an hour and Mark made $15 an hour. And then I can figure out that they each got a 6% wage increase. So I can figure out that Jack got $21.20 and Mark got $15.90 an hour. And that gets me to 530 more. And so that would be a single possible answer, right? I can answer the question when I know everything. The trick of the C trap is that I don't need to know everything. If I know everything, I can answer the question, of course. But the GMAT loves situations where you can answer a question without knowing everything. And it's all in this stuff up here, all this extra stuff. Yeah, you can build a lot of inferences from it. You can make a lot of inferences. You can figure out what their actual amount, you know more when you bring the two together. I know what their actual wages are and become, are or were. But I never needed to really know that. That's not what they asked. And just by taking this path, can I get to one possible value that they ask for? And so the answer to this question is A. And so where was the moment that gave people the most grief, or what caused you, if you said statement 1 was not sufficient, which many of us did because we chose C, what inference was it that caught you, that you should have made that you didn't because you said it was not sufficient when it was? It's probably this one. That's probably the inference that you didn't make. And if you don't make that inference, it's very hard to get this question right. It is still technically doable if you really test cases, but one thing we also I like to talk about using inference maps is that testing cases is a good way to get an answer. And it's a super strong method. I highly recommend using it. But when you make an inference map, as I showed you, you can use testing cases, but you can also often avoid testing cases. You can actually show what inferences can be made and which ones can't. I'll show you another example of that here in a second. So when you're reviewing a question, when you're reviewing data sufficiency, lay out, again, if you missed that something was sufficient, lay out the inferences that get you to sufficiency. Which one did you miss? If you said that statement 2 was sufficient, if somehow you ended up on statement 2, if somewhere you ended up to, oh, there's only one possible value. If I know the ratio, I know what the difference is. What inference did you make that you shouldn't make? Somewhere in your in your reasoning, there was an arrow that you shouldn't have drawn, metaphorically. Figure out where that was and why you shouldn't draw it. Let's take a look now at this data sufficiency question here. Oh, that's the one I just did. Take a look at this question here. Take 2 minutes. That's 2 minutes. $2:20, $2:30. All right, final guesses. I have an E, a C, a D, a B, an E. All right, so kind of a hodgepodge of answers here. So let me show you how I would have done this question the first time I did it. Okay, I would have said, all right, I know that n is m cubed minus m. I know that k is less than 10. I know that we have positive integers. That's great. I want to know, oh, you know what, also, I mean, it's basically the same question, but I didn't mean to ask for the remainder. It's honestly, this doesn't change much, but I wanted this to be, is n divisible by k? That actually I gave you a slightly harder version of the question. The answer is the same either way, for what it's worth. This doesn't change the answer. So if you'd gotten this one right, you would have gotten this one right, and vice versa. So it doesn't change much. But I wanted this to be a yes/no question, and I'll explain why in a second. So I want to know, is n divisible by k? Is n divided by k an integer? Question mark. That's a yes/no question. That's a little bit different. The last question we were asked was, what is the value? And I know this one I asked that as well, but I didn't mean to. If a question asks for yes, no, that's a little bit of a different game. Because I'm not looking for a number, I'm looking to answer yes or no to a question here. And if this were the day I took the test, I don't know what else I would do here. I probably wouldn't do much. Statement one, you'd tell me, hey, m is 5, and I'd go, great. Then n is 125 minus m. It's 120. Okay, okay, that's nice. So 120, what could k be? K could be 5. And then the answer is yes. N over k is an integer. N is divisible by k. But I could also do 120 over 7. And the answer is no. 120 is not a multiple of 7. And so this is called testing cases. There's a full GMAT prep hour on testing cases. It's one of the most important, powerful strategies on the test. If you haven't watched it, watch it. Get testing cases down. But this tells me that statement 1 is not sufficient, so I'd get rid of A and D. Statement 2 tells me k is the product of 2 distinct prime integers, and k is less than 10. So I'm thinking of, okay, what prime numbers multiply less than 10 that are unique? And 2 times 5 is 10, so that's too big. 2 times 3 is 6. 2 times 2 is not distinct. 3 times 3 is not distinct. And here's an important thing. 1 is not prime. So a piece of trivia for you to remember about the GMAT, 1 is not a prime number. So this actually tells me k is 2 times 3, which is 6. And my first thought would be like, yeah, well, I don't know what n is. I don't know what m is. This can't be sufficient. But I would still, because I know the test, I would still test some cases. I'd say, okay, but what if m is 2? Then n would be 2 cubed minus 2 would be 6. And is 6 divisible by 6? Yes, 6 is divisible by 6. And then I'd say, okay, what if n is 3 though? 3 cubed is 24 minus 3 is, 3 cubed is 27 minus 3 is 24. Hey, that's also divisible by 6. And actually, if m is 5, I already know it would be 120, n would be 120, and that's also divisible by 6. And it's test day and I'm lazy. I'm going to say statement 2 is sufficient and move on. That's it. I'm going to just guess. I've gotten the same answer 3 times on different cases. I don't know. I guess it's probably always, I guess n is always divisible by k. How strange. I'll move on. That's what I would do on test day. But when you're at home studying, you might be like, but why? Why is n always divisible by k? And you should study and you should review and figure out how this question works, even though testing cases is a great strategy to have. Curiosity is going to be your good friend, and you can lay out a few different things here. So if we build an inference chain for statement 1 alone, first thing to note is that this is a yes/no question. The outcomes I'm curious about when I'm dealing with a statement or a combination of statements is the answer always yes? The answer is always no, or I can get different answers depending on the numbers. Yeah, Sonia, that's it. Very good. Okay, we'll show that in a second. So statement 1 alone tells me m is 5. Well, when I combine that with n is m cubed minus m, I get that n is 120. And then let's just test cases. Again, 5 and 7. If k is 5, n is divisible by k. If k is 7, n is not divisible by k. And so I've proven, this is proof, right? I've proven that I can get different answers depending on the different numbers. And you can just, in general, you can pretty much assume that if you know 120, if you know some number divided by x, you don't know if 120 is a multiple of x, if you don't know anything about x. You have no idea. It could be a multiple of x, or it could not be. That's just not going to be enough. There's multiple possible answers. Okay. But if I go to statement 2, and this is the sneaky thing. If I look at that m cubed minus m, I could factor out an m and get m times m squared minus 1. M squared minus 1 is a difference of squares. I can turn that to m plus 1 times n minus 1. So I end up at n equals m times m plus 1 times m minus 1, which is a product of 3 consecutive integers. this might be the chain of inferences that kind of you didn't see. I wouldn't blame you. I wouldn't have seen it either. But you can look at these errors and say, okay, why would I do that? Well, I have a common factor here, and difference of squares are always nice. The GMAT likes difference of squares. I filled out more of that chain than I meant to, didn't I? I just got ahead and shown you the whole thing. That's fine. That might be the moment that caused you the grief. Could be this getting to 3 consecutive integers. Even then, it's still not easy, because once I know n is a product of 3 consecutive integers, it's another thing to know that that means n is a multiple of 6. Maybe that inference gave you some grief. But if n is a multiple of 6 and k is a number that is a product of 2 distinct prime numbers and k is less than 10, k is 6. So if n is a multiple of 6 and k is 6, n is divisible by 6, and the answer is always yes. I can answer that question. The way I tested cases, when you test cases and you end up saying, like, I don't know, I guess it's sufficient because I've tested cases and I keep getting the same answer, you're really not proving sufficiency. You're just kind of saying, I bet that this is the answer. And that's not to say it's not a powerful strategy. It is a very powerful GMAT strategy. But it's not really making a last inference. You're just kind of making a guess dotted line to the answer is always yes. You kind of are saying, like, I'm pretty sure the answer is always that yes, and I'm moving on. That's what you often do in testing cases. But when you're reviewing, you can dig in and be like, okay, but why is the answer always yes? What is it about this situation that makes every case possible an answer of yes? And this is the reasoning chain why. Now, you might have trouble with those red arrows, or maybe it's this jump. Hold up, the product of 3 consecutive integers is a multiple of 6. Why? Well, you can break that down and really figure out what's going on there. And this is just some quantitative facts. Multiples of 3 happen every 3. Multiples of 2 happen every 2. So in 3 consecutive integers, I'm guaranteed to have a multiple of 3 and a multiple of 2. And if you have the product of 3 consecutive integers, you have a multiple of 3 and a multiple of 2. That's a multiple of 6. But as you study that and practice it, you kind of end up just back at, like, okay, yeah, but I can just actually just jump right to n as a multiple of 6. Yeah, Jocelyn, on the question I originally asked, it's the same idea. The answer would still be B, because the remainder would always be 0. So the end, it's very similar game at the end of the day. You recognize, oh, this number is always divisible by 6, so this number always has remainder 0. So I guess B is sufficient. Statement 2 is sufficient. But again, look at the inference that gives you gunk, and if you need to study it, figure out like some sub steps, some sub inferences. And once you've done that and understand it better, you can go back to, okay, now I see why someone could quickly say, oh, the product of 3 consecutive integers is a multiple of 6. You can build your little shortcuts. Okay. Let's do this one here. Take 2 minutes into ref and slope territory. 2 minutes. I have an E, a B, and a C in. Another E. Another C. Okay, I'll call it there for the sake of time. And also for the sake of time, I'm going to just show you the inference chain that you could build from this. Again, you wouldn't build the chain in the test. This is a review tactic. And you wouldn't even build it immediately after you try the problem. You would read reviews and figure out, how you would organize the question. But then as kind of like a final bow on it, you'd lay out the inferences that are made. Okay, and ID the ones that give you the most grief. So first off, this is back to a value question. So there's two possible outcomes to situations we're analyzing, that there's one value for the y-intercept or there are multiple possible y-intercepts. Those are the two possible outcomes that I'm curious about. I'm not given much up front. I just want to know what is the y-intercept of line L. Statement 1 gives me that the slope of L is 3 times its y-intercept. And I could test cases here. I could say, okay, well, if y-intercept is 4 and the slope is 12, or the y-intercept is -2 and the slope is -6, and that's multiple possible values. Testing cases does let you infer not sufficient because you can show 2 possible cases. So I could test cases, but there is another approach here using algebra, right? If I know the slope of L is 3 times its y-intercept, another way of writing that is m equals 3b. And by m, I mean the slope, and the b, I mean the y-intercept in slope-intercept form. This is the equation of a line relating the points on the line to its slope and y-intercept. If you need to review that, check out the resources out there for graphic geometry, for coordinate plane geometry. But if the slope is 3 times the y-intercept, I can put that into the equation. I can say that y equals 3bx plus b. And since I want to know the y-intercept, I know that's where x is 0. That's the definition of y-intercept. And y is the y-intercept. Y is b. So I can plug in the coordinate. I can plug in 0 for x and b for y. And that tells me the very wonderful information, b is b, which is very boring and doesn't let me know what b is. It tells me b is what it is, but what is it? Could be 2 and 2, could be 3 and 3. B is b. Not enough to answer the question. So I would get rid of A and D. Statement 2 tells me that the x-intercept of the line is -1/3. And that, I mean, I could have infinite different y-intercepts, right? If the x-intercept is -1/3, okay, y-intercept could be anywhere. There are multiple possible values. But again, I could do some algebra here as well. Because at the x-intercept, the y value is 0. And so I know that one of the coordinates on this line is -1/3 for x and 0 for y, and I can plug that into my equation of a line, get that 0 is m times -3 plus b, which tells me m over 3 is b, with just a little bit of rearranging. Which, if I'm just thinking about algebra, I don't know. That's 2 variables, 1 equation. I don't have an answer. I cannot tell you what b is. Could be m could be 6, b could be 2, m could be 9, b could be 3. I don't know. 2 variables, 1 equation is not enough. So for the first time tonight, I think we actually need to bring the 2 statements together. We have to test now, are they enough together? Well, that first one algebraically, the slope is 3 times its intercept, tells me m equals 3b. What do we notice about this inference chain now? Is this going to get me ultimately to one possible value? Why so, Jocelyn? Sonia says both statements give me the same info. One variable, one equation. I see one variable, I see one equation, 2 variables. at least in statement one's information. Here's statement two's information still up here. Notice m equals 3b is the same equation as m over 3 equals b. Yeah, Sonia, you see it. This information is actually right here in statement two's information. And so the two situations, the two statements actually converge before they can give me a single value. They end up on the same inference chain that leads to there are multiple possible values here. And that is the case. This is a situation where the answer is E. I cannot answer this question because I actually have the same information twice. The inferences I can make from statement two are the same inferences I can make for statement one, that m equals 3b. Which is a cool equation to get, but it doesn't tell me what the y-intercept is. So here we have an answer of E. The inference chain does not collapse to one value. Okay. So those of you that said it was sufficient, where did you drew an arrow that you shouldn't draw? Was it just because you just felt kind of like, I don't know, I got two pieces of information about the graph, so I guess it's sufficient? Was that the inference you drew, like two pieces of information, sufficient? Well, it might be if there were two different pieces, but it's not two different pieces. This is actually the same piece. It's just hidden well, as is the GMAT's way. Okay. One last question here. Take 2 minutes. I'll show you the inference map you can make for this one. That is 2 minutes. Go ahead and make a guess. I have a B, I have a C. I have another B. This is a hard question, by the way. We've seen a few hard questions, but this one in particular is a doozy. So first off, it's another yes/no question. So we're wondering what outcomes could we have in the situations we're considering? Is the answer always yes? The answer is always no, or the answer depends on the circumstances. Could be either. Those are the three kind of outcomes I'm curious about regarding the inference chain I build. So this is also another good example of the importance of doing some work up front. Very often, the most important work you can do in a data sufficiency question is early in the question itself before going to the statements. We can make quite a few inferences here, or at least we can lay out some possible worlds. If x times y plus z is odd, okay, well, a sum of two numbers is odd if one is even and one is odd. So I can infer that either xy is odd and z is even, or xy is even and z is odd. Those are the two possible worlds. So now let's break into these two worlds. Let's chase both of these rabbits. Let's first start thinking about the one where xy is odd and z is even. Well, I know another rule about even odds. A product is odd if both integers are odd. One thing I should have mentioned by now, forgive me, is that you have to notice when you build an inference chain where you are using information they give you and where you are expected to bring in something, where you are expected to just know something about a situation or about math that's relevant to the situation at hand, right? And you want to highlight, make sure you know whatever thing it is that kind of you need to make the inference, whether it's a rule or just an equation, whatever it is. But if xy is odd and a product is odd if both integers are odd, then in this situation, x and y are both odd. Okay, so great, I have one situation. Z is even, x and y are both odd. Okay, now let's go to the other branch where z is odd and xy is even. Well, a product is even if one integer is even. So if xy is even, and that happens when one integer is even, either y is odd and x is the even one, or y is even and x is anything. And what you can do is you can chase these rabbits, make these inferences in these different possible branches, and realize that ultimately you have three worlds here. Either z is even and x and y are both odd, or z is odd and y is odd and x is even, or z is odd, y is even, and x is question mark. You wouldn't be able to know. But those are the three worlds up top to think about that you can get to, that you're in. And so what I'm going to do here is I'm going to take this inference chain this is all the pre-work inference chain I've done, and I'm going to take the outcome, those three possible worlds, and I'm just going to put it up here as a reminder of the three possible worlds. I'm going to call it scenario A, B, and C for the sake of space. Right? I know up front that I have one of these three worlds. So let's look at statement one alone. Tells me xy plus xz is even. Well, I can factor out the x and say x times y plus z is even. And again, I bring in a rule about multiplication. That means that either x is even and y plus z is whatever the hell it wants to be, or y plus z is even and x is whatever the hell it wants to be. One of them must be even. Could be both, but one of them must be even. If y plus z is even, I have another rule. A sum is even if both numbers are even or both numbers are odd. So I have another branch. Either y and z are both even or y and z are both odd. Well, let's see if these are possible. Are y and z both even? If I look up here, Z is even, Y is odd. Z is odd, Y is odd. Z is odd, Y is even. I never have a case, there's no scenario where Y and Z are both even. So in this world, down here, I need Y and Z to be odd. If Y plus Z is even, then I need both Y and Z to be odd. Well, if Y and Z are both odd, that happens in scenario B. Sorry, I meant to mention here, right? Okay, if X times Y plus Z is even, if X is even, I'm done, right? That's what I want to know, is X even? It could be. Here, X is even. Done. The question is, what happens to X when Y plus Z is even? Well, there's two scenarios, but one of them is not actually a scenario because it's not consistent with what is given. So we actually realize that we're in scenario B, and in scenario B, X is even. So I end up in a world where either X is even or Y plus Z is even, in which case Y and Z are odd, in which case X is even. X is always even. Under the constraints I'm given, X is even in this situation. The end of every possible chain ends with X is even. And so the answer is always yes. This statement is sufficient. It's a lot of considering possible splits, right? You have to consider that this is the case, that this is the case, okay? That this is the case, that this is the case. But if you consider and you use your rules of even odd, you realize, and if you've specified what worlds are possible up front, if you don't have this is even trickier. But you're going to realize that you're going to end up at an even X. And if I go to statement 2, where Y plus XZ is odd, well, when does that happen? When one is even and one is odd? Okay, so let's consider Y is odd and XZ is even. Well, XZ is even if one of them is even. We've seen that rule before, so either X is even or Z is even. If X is even, I'm done. X is even. If Z is even, I'm in scenario A. And in scenario A, X is odd. So I'm already done. I'm technically done with this statement already. I don't have to consider this other path. I'll show you what it looks like in a second, but you don't need to chase it. In this world, I can have X be even and be in scenario B, or I can have Z be even and be in scenario A where X is odd. So I don't have an answer. The answer depends on the circumstance. But again, the value of mapping this out is to show you what your logic has to do and where you have to consider different possibilities and where those branches take you. And then, okay, what is the best, because you wouldn't actually draw this on the test. How would I organize this? What should I draw to make these inferences? Could I use a table? Could I use a chart? What am I going to do to make the inferences I need to get to the point where, okay, in statement 2, I have 2 possible outcomes for X. In statement 1, I have 1 possible outcome. It's pretty sneaky, but I end up that X is even. Okay. If you did want to chase the inferences here just for fun, you could say Y is even, XZ is odd. Well, if XZ is odd, they're both odd. If X and Z are both odd, you're in scenario C. So X can be odd. Okay. Is this not a test case question? Marilyn, I kind of am testing cases. I'm just not testing numbers. I'm testing kinds of numbers. I'm testing even and odd instead of 2 and 3, but that's fine. Even and odd works for every even and odd number. So I just consider the categories of number here. And I actually think it's a little bit less of a pain to have to test actual numbers than to test kinds of numbers. All right, so for statement 1, where's my statement 1? All right, for this hellish looking statement 1, I would deal with x is y plus x times y plus z is even. And I want to know if x is even. Well, okay, x is even, so I'd be done. I don't even have to consider that. The question is what happens when y plus z is even? Well, either I have y odd and z odd, or I have y even and z even. Those are the 2 times that y plus z add up to even. And then, okay, if y is odd and z is odd, z is odd, y is odd, I'm in scenario B, so x is even. If y is even and z is even, y is even, well, z is even, y is odd. So this dies on the vine. So this is probably what my work would look like on the test. And it's testing cases, it's just testing kinds of numbers rather than testing actual numbers. But it helps me make the inferences I need. X is even, hey, the answer is always yes. All right, gang. Those are inference chains in the context of data sufficiency. Again, it's a way to make you think really deeply about the logic that you're doing on a question, which will just help you think deeply about the GMAT in general. You can also check out the inference chains and problem solving video for tactic and examples of working through problem solving. It's a similar idea, but in data sufficiency, it's more about can you build a chain with the information rather than do you know the exact answer to the question? Although, as we saw, often you still answer the question anyway in data sufficiency. There are other free options out there, as we talked about. Check out our link, manhattanprep.com/gmat/classes, Foundations GMAT Math course. We have 2 of these free prep hours a month or so, and we have a whole library online. Hope to help you in any way we can. Otherwise, best of luck in your studies. Be in touch, and we'll see you next time.